Welcome to Math with EJD. In this video, I'll start with numerical optimization techniques with an introduction. And you can see it as a continuation of the playlist on numerical analysis. But I think it's better to separate this particular one on optimization, although it's still about numerical techniques. So I might end up adding this playlist to that one. But I mean, it will also stand on its own for easy referencing. So introduction to numerical optimization techniques. We go first of all for an overview. So numerical optimization techniques play a crucial role in solving mathematical problems where analytical solutions are either impractical or impossible. So there are cases where the solution to a problem is even more difficult than the problem itself. I mean, talking about the analytical solution. So, or sometimes the solution is totally impossible. In those cases, we resort to numerical methods. So, these methods are widely used across disciplines such as engineering, economics, machine learning, and applied sciences to find optimal solutions. That's best solutions to find optimal solutions while considering constraints. Okay. Um, Optimization problems typically involve minimizing, minimizing, or maximizing an objective function with respect to certain decision variables. Okay, so having said this, let's look at some key techniques. So numerical optimization techniques can be categorized into some key aspects, which we are going to see one after the other. So we talk about key numerical optimization techniques. So first of all, we have a group of techniques that we can refer to as gradient-based methods. Gradient-based methods. That means that they involve the use of derivatives. So gradient-based methods. So gradient-based techniques, gradient-based techniques utilize derivative information. Derivative information. So that means any expression that is not differentiable, we can use this method for them. So gradient-based techniques utilize derivative information to iteratively, update decision variables, decision variables, and converge toward an optimal solution, toward an optimal solution. So let's see some examples of this kind of methods. So all the examples that involve derivatives automatically fall here. So we have the gradient-based methods, like I said. So let's have the first one. Okay, let me say examples. Examples include, say A, or let me use the nicer kind of pen. Okay, so examples include what we call the gradient descent. Gradient descent. So it's more like you're climbing down gradients. That's the idea that conveys. But let's see. So this is actually this is a first order optimization method. A first order optimization method that moves in the direction of the negative gradient, the direction of the negative gradient. So that's why it's a descent, right? In the direction of the negative gradient to minimize an objective function. An objective function. So it is expressed as, now this, so it is expressed as xn plus 1 xn plus 1 equals xn minus alpha nabla f of xn. Okay, so it requires gradient. So once you see this, you know some kind of gradient talk is going on right there. So that's one of the methods under gradient-based methods. Then we have another example, which is called the Newton's method. Now, this Newton's method bears close resemblance with the Newton-Raphson method for root finding. But here we are talking about, we are not just talking about root finding, we are talking about optimization. So, but if you look at the formula, they have a kind of similarity. So this is actually a second order method. You know, gradient descent is a first order method. So Newton's method is a second order method that incorporates both the gradient, and the Hessian matrix. So you see matrix is coming into this now. And the Hessian matrix. The Hessian matrix is a representative of the second derivative. Second derivative for faster convergence. And you also bear witness to the fact that when we talked about root finding and we're using it in Raphson method, in fact, about the fastest of all the methods, because we use the function and its derivative. But here we go even to the second derivative in the case of optimization. So the formula is it's usually iterative. You have xn plus 1 is equal to at a state before it minus second derivative, that's delta squared f of xn. Should that be delta or nabla? Nabla squared f of xn inverse multiplied by nabla f of xn. So it's more or less like what we have in under root finding, except that here we're talking about matrices instead of just ordinary functions. So this is it. So you can see this is like first derivative, second derivative. This is a function, then the second derivative. So with that done, we have two examples of oh, okay, I didn't even write it. I think I was in a hurry to talk about it. Newton's method actually is the second one. Newton's method, which is a second order method that incorporates both the gradient and the Hessian matrix, which is the second derivative, for faster convergence. For faster convergence. Okay. So we have a third one, which is also popular. Let me do it this way now. So call that C. So we've talked about gradient descent, we've talked about Newton's method. Now let's mention the conjugate gradient method. Conjugate gradient method. So the conjugate gradient method is also a gradient-based method. So what this does, it actually extends it, should I say, this method, this method extends gradient descent. So it takes gradient descent further. This method extends gradient descent by using conjugate directions. By using conjugate directions for faster convergence. For faster convergence, especially in large-scale problems. In large-scale problems. Okay. So as the methods progress, the convergence gets better. So those are examples on that gradient-based methods. So another set of techniques are what you can call the derivative-free methods. So it is not every function that will be differentiable. Okay, so in that case, you may be able to use derivative-free methods where we don't need gradients, we don't need to be able to differentiate a function. So derivative-free methods are these techniques are useful. They are useful when derivative information and derivative information is unavailable, is unavailable or unreliable or unreliable, making them suitable for complex, noisy, or black box functions. Black box functions. Okay. So this include, again, we go for that order. So here we have what you can call the Nelder-Mead method. Nelder-Mead method. Oh, okay. I'm sure this is not a popular mead in sociology. The Nelder-Mead method, which is a heuristic optimization method that iteratively refines a simplex, it refines a simplex of candidate solutions okay, and it is commonly used in optimization problems with noisy or noisy, right? Or non-differentiable, noisy or non-differentiable objective functions. Simply, when you cannot differentiate a function, then you should be thinking about derivative-free methods like Nelder-Mead method. So another of this method would be the genetic algorithm. So you can see the idea of genes coming in there. So genetic algorithm or GA for short. Okay. So this is inspired. This is inspired by natural selection. By natural selection, a concept in biology, right? By natural selection. So it evolves, it evolves a population. So you see evolution coming in there. It evolves a population of candidate solutions, of candidate solutions through selection, through selection, crossover, and mutation. Okay, so that's the idea of genetic algorithm. It is suitable for complex, high dimensional, and non-convex problems. Non-convex problems. Very soon you'll be introduced to the idea of convex problems. So I mean, as we go on in this series, we are going to pick these methods one after the other and talk about them. Okay, so that's genetic algorithm. So apart from genetic algorithm, another derivative-free method would be the simulated simulated annealing. Okay, so that's C now under derivative-free method. Yeah, under derivative-free method. So we have what you can call the simulated annealing. So it's an idea from, I think, metallurgy, simulated annealing, SA. So, so it is a probability technique. It is a probabilistic technique that explores that explores the solution space, it explores the solution space, occasionally accepting, occasionally, occasionally accepting worse solutions, occasionally accepting worse solutions to escape local minima. All right. So that's the second group. So first group is gradient based. Second is derivative free, which is more or less like non-gradient based, if you like. And then we have a third group of problems we'll be considering under numerical optimization techniques. And that would be the constrained optimization methods. Constrained optimization methods. Constrained optimization methods. So for constraint optimization method, these methods ensure that optimization, the optimization problems respect equality, and inequality constraints. Okay. So um examples include examples include the very important concepts of Lagrange multipliers. So you have Lagrange multipliers. So this is a mathematical approach. This is a mathematical approach for incorporating constraints into optimization by introducing auxiliary variables. By introducing auxiliary variables. Auxiliary variables. Okay, so it is used when constraints are differentiable. When constraints are differentiable. So you have to be able to differentiate the constraints to use Lagrange multiplier. Okay, so that goes. Apart from that, we have also the what's it called? The sequential quadratic programming. Sequential quadratic programming. And for sure, that is SQP, sequential quadratic programming. So here, this solves a series of quadratic programming, a series of quadratic programming subproblems, a series of quadratic programming subproblems that approximate the original nonlinear problem. The original nonlinear problem. It is effective. It is effective for constrained optimization. Widely used in engineering, design, and control systems. Okay. We also have the interior point methods. Interior point methods. C, interior point methods. Still under constrained optimization methods. So what do interior point methods do? First, they transform they transform constrained optimization problems into a series of easier problems by adding barrier functions to prevent constraint violations. Then they are efficient. They are efficient for large scale, non-linear programming problems, That's NLP problems. I have a whole playlist on linear programming problems. So talking about simplex method and so many other methods like that. Okay, so we have seen the third category of problems. That's constrained optimization problems. So we have a fourth category. So we are in for a very comprehensive experience. We have a fourth category talking about convex and non-convex optimization. Convex and non-convex optimization. Okay. So first of all, we talk about convex optimization. Convex optimization. Or better still, let me just do this now. So let's talk about convex optimization. Convex optimization. So it involves an objective function and constraints that form a convex set, ensuring any local minimum is a global minimum. So it is typically solved. It is typically solved using gradient-based. So I mean, here we are solving the problem here using a method that has been mentioned before, using gradient-based or interior point methods Okay. Then, of course, we have the non-convex optimization part of things. So, non-convex optimization. So here, solutions may get trapped. Solutions may get trapped in local minima. So you see, we saw sequential. We saw a method before that will even violate some rules just to escape local minima. So solutions may get trapped in local minima requiring stochastic or heuristic techniques. When we talk about non-convex problems. Okay, so methods like the methods we use here, methods like particle swarm optimization, that is PSO for short, and simulated annealing, which was already mentioned before, simulated annealing, which is an idea from metallurgy. Yeah, I think it's simulated annealing that tends to get out of character just to escape minima, local minima. The idea of local minima is that, in a particular region in a function, right? If you we can have many minimum points, but the smallest of them is the local minima. But if you get to other regions, you may find other minimum values or and all that, right? So but when we get into it, we'll explain better. And simulated annealing, PSO and simulated annealing, SA for short, are useful for escaping local minima, local minima. Finally, let's talk about another category of numerical optimization techniques. So, and that is, we have some techniques that are specific to nonlinear programming. So I can make that my fifth category, right? um Fifth category, that is non-linear 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 programming, that is NLP, non-linear programming specific techniques. So these techniques are specific to non-linear programming. So I mean, there are other methods that you can use for both linear and non-linear programming, but these methods we want to mention here are basically for non-linear programming. So um non-linear programming, NLP, extends these optimization techniques, these optimization techniques to problems where the objective function, or constraints are non-linear. So key NLP methods include okay, as we've been doing, it includes what you can call penalty and barrier methods. Penalty and barrier methods. So this penalty and barrier methods, this convert constrained problems. They convert constrained problems into unconstrained ones by adding penalty terms for constraint violations. Okay, so that's one method under nonlinear programming. Another one would be the okay, I think this is not even necessary, right? Another one would be the Karush the Kontoka, Karush, Kontoka, KKT, the KKT conditions. Karush Kontoka conditions. So this is a generalization. This is a generalization of Lagrange multipliers, providing necessary conditions for optimality in constrained nonlinear programming problems. Okay. Then finally we have evolutionary algorithms. Evolutionary algorithms. Okay. So these are algorithms. These are algorithms like genetic algorithm, and differential evolution and differential evolution. Algorithms like genetic algorithm and differential evolution are often used for complex multimodal NLP problems. Okay. So, I mean, in conclusion, right, you see that numerical optimization, including nonlinear programming, is essential for solving real-world optimization problems across multiple domains. While gradient-based methods work well for smooth functions, okay, I guess I want to write that down. Very important. So we are talking about conclusion now. So point one, gradient-based methods work well for smooth functions. That's one point right there. And another point is that derivative-free and heuristic techniques help tackle complex, noisy, or constraint problems. Okay. So choosing the right optimization method depends on the problem structure, computational constraints, and the desired accuracy of the solution. I think that's also a very important point to note. So choosing the right optimization method depends on the problem structure. What does problem look like? As the problem structure, computational constraints, constraint like whether you need a derivative or not. So if the problem cannot be differentiated, then you cannot use a derivative, a gradient-based method. So computational constraints and the desired accuracy of the solution. I mean, this has been a long video already. If you have subscribed to the channel, thank you for that. If you have not, go ahead and do that because there's a lot to come. So I'm going to take these methods one after the other and break them down for for your proper understanding. So subscribe and hit the notification bell so you can always get alerted each time a new video is released. Then comment, let me know how helpful those videos are, and let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. Don't forget to like and share so that more people can have access to this great content. Till I come your way again, keep optimizing everything in life. Bye.